All right, so good morning and welcome back to
This
Computer
meeting is being
Architecture.
recorded.
Oops, let me start my video. All right, there we go. So today we'll just do a short review of Appendix A, chapters 1 through 3, using a review sheet as the basis for where we are. But before we do that, let me get to the administration of the test. Wrong button. All right, here we go. Okay, so today we've got the review. Wednesday we have the first exam, and then we'll have spring break. And then the chapter 3 homework is not due until after spring break. And then we'll dive into the rest of the textbook, chapters 4 through 6. For the test, what I've been doing is there's no password on the test. So once it unlocks at 8 a.m. on Wednesday, it'll be available all day. And so there's also no lecture or class meeting. Instead, I'll be available through Google Chat during the day. The test has 25 multiple choice questions, 10 points each, and it's open book. And so we'll take a look at the review sheet posted under the review exams review link. The exams themselves will show up here on Blackboard under the exams link, and I don't use Respondus or any of the other special locking software. It's just a regular Blackboard test. One technical note I'll mention is don't leave the test unattended. Once you start, finish the test, because if you step away from Blackboard and it times out, then what generally happens is then the test gets submitted automatically when Blackboard times out. And if you haven't completed it, then you'll have unfinished work. And so then you would have to contact me and get me to reset the test. So I'm giving you plenty of time throughout the day that you can either pick the class time, plus, originally we had, because this is sort of a push to put the class online versus in the classroom. So there's a large window of time available, but you can also pick a better time in the morning or afternoon or evening to knock out the test. So any questions on the administration of the test? Okay, and then don't forget I do have recordings of the earlier classes, so if you ever want to go back and review those, you can do so. I guess that would be under recordings, right? Okay. So what I thought I'd do is there's basically 4 sections of the review, 4 sections of the test. There's chapters 1, 2, and 3 and Appendix A. The most questions come from chapter 2. There are 10 questions from chapter 2, which then leaves 5 questions for each of the 3 other chapters / appendix, adding up to 25 questions in total. So 5 from chapter 1, 5 from appendix A, then chapter 2 has 10, and then 5 from chapter 3. And then for the review sheet, I kept it kind of slightly high level, so not individual items. Instead, what I highlighted in the review sheet were sections in the chapter to focus on. If there is a dot in front of the heading, such as benchmarking for CPU performance, then that's not a section heading per se, but that's a topic that I also think is worthwhile to mention for, and that will show up on the exam, right? So, for example, benchmarking for CPU performance, Boolean logic, a discussion of some of these other topics, right? So not a heading. I emphasize that down here at the very bottom. So let's work our way through. So 8 great ideas in computer architecture below your program, technologies for building processors and memory, and benchmarking for CPU performance. So if I start with the first 2, 8 great ideas in computer architecture and below your program. Let's see. So we've got our 8 great ideas, Moore's law, abstraction, common case, parallelism, pipelining, prediction, hierarchy, and dependability. These will show up throughout the rest of the other chapters. That's why I view them as something important to be familiar with. Moore's law, the doubling of transistors every couple of years. Abstraction, being able to break out differentiate between the transistors, the logic, the instruction set architecture, the operating system, the applications. And then when you're looking at performance, the next 4 are focused on that. Where should you look at the performance? In that, 80% of your code that runs a lot rather than the less common pieces that run once. And in the various chapters, chapter 6, parallelism, chapter 4, pipelining and prediction. We'll talk about those more in depth. Chapter 5 is hierarchy of memory, and dependability via redundancy. We'll talk about in chapter 5 in more depth, right? But the fact that there's these great ideas. As I mentioned before, abstraction allows you to break out your program, your computers into layers, right? And so those are fundamental courses. We've dealt with high-level languages for our applications. To build our programs, we've got our compilers to run or manage the resources that our programs need. We've got the operating system, which also manages all the rest of the hardware, right? And then what we're talking about in this course is, of course, the hardware, the processor, and the memory system. And then the fact that we have a processor, the instruction set architecture, a place for storage, a way to communicate, and that we're building these things out of silicon, along with additional materials to build conductors, insulators, switches, transistors. Let's see. And then the last major thing from chapter 1 is then this idea on performance and performance analysis, right? And benchmarking. And so we ask about throughput, but we really focus in chapter 1 and in this first part on response time. How long does it take to do something, right? And then in a benchmark, we do relative performance. So we sit there and say, well, given this old hardware that runs it in 10 minutes, does the new hardware run it faster, right? In 6 minutes, so or 5 minutes, so it's twice as fast, or it's only 1.5 times as fast. And it then becomes a little bit of a challenge to figure out, what do we mean by all that? Are we talking about our program? Are we talking about the operating system? Are we talking about the hardware? What parts of these? And we try to separate those out so that we focus on the CPU time and our user time. And part of this comes down to looking at the count of instructions for our program, which is based on the instruction set architecture, how well the compiler can take our code and translate it into the instruction set, and the realization that the different types of instructions may have different cycles per instruction, right? We remember seeing that, for example, if I look at that history of the ARM, just as an example, we can see that different instructions have different times, right? And this is just an example from the x86. So he used a more generic example where he didn't try to categorize them as floating point or branch instructions or logic instructions. Instead, he just had classes A, B, and C to demonstrate this idea. But so therefore, when we're looking at benchmarks, we're looking at the algorithms, the programming language, the compiler, the instruction set architecture. And then we look at benchmarks for certain categories, such as power consumption, single processor performance, multi-processor performance. So you can see that in some of the modern benchmarks that are out there, right? And there are other ones that are out there that are freely available if you're interested in looking at that for your own machine. But the one that he looked at was the CPU benchmark from the spec.org website. I think, right. And the idea that the performance is more than simply a simple count of the speed of the computer. There's also the instruction set, the CPUs, multiple CPUs for parallel systems. All of these come together to differentiate the performance of machines between other machines. So, any questions about chapter 1, other than what else I'd already said? Okay, so let's move over to Appendix A. So a few less topics here. The main thing is to be interested in is sort of the Boolean logic and the standard form. And so this idea that we have this Boolean algebra, and then be familiar at a high level, right? The Boolean product, which is the AND gate or the AND operator, the Boolean sum, which is the OR operator, and then the Boolean NOT. This idea that there's a Boolean function comprised of a set of all of these to do a specific equation. Don't need to worry about any of these identities. So we can skip that. And then this idea of the standard form, so that if I have something like this truth table here, I know that I've got 5 terms. And the terms that I have, those 5 terms, are the ones that end in a 1 for the standard sum of products. And so I've got 5 terms. I've got x naught, y, z naught for the first term, x naught, y, z for the second, x not y, not z for the third, and then x, y, not z for the fourth, and for the final term, x, y, z. And I put those together. They're all ANDed together with the not symbol for the ones that were zeros, and then they're ORed together. So sum of products. And that's the only one to worry about. The product of sums, we won't concern ourselves with on the exam. So,
and not only this, we need to know how to simplify it as well.
No, I left the simplification and the K-maps off the test. That's only from the homework, right? So don't worry about the identities, and don't concern yourself with the K-map stuff. That was from the homework. Plus, it's not, the K-maps themselves are not in the textbook, so I didn't want to put them on the test.
Okay, thank you.
So we can skip past all of those, right? And then the other idea is, let's see, make sure. This idea, so the last topic here on the Appendix A is combinational logic. And so the idea here is that we have some logic. It has inputs, and then near instantaneously, you get a result from that. And then that all has to occur before the next clock cycle. And then you maintain the state from clock cycle to clock cycle of the state of the logic from each of these circuits. Right? Our inputs in this particular one, A, B, and our various outputs. And the state of the outputs is based on the state of the inputs, and that is generated each clock cycle. Though it doesn't take a full clock cycle for a lot of these logics, they pretty much run near instantaneously because these things are moving through at near the speed of light. All right, so chapter 2 is a bit longer because there's a bit more material to cover as part of this. But the overarching idea is this idea of having to take everything we've talked about in the previous chapters and encapsulate them at a new layer of abstraction with an instruction set. And that instruction set has to deal with data. So there's a brief section on data, communicating with people, representing instructions, twos, complements, signed and unsigned numbers, and then also a discussion of where we're going to hold that data in a set of registers, right? And so we take a look. Wrong button. All right. All right, so we have different instruction sets for different architectures. The one we're focused on is the ARM instruction set, which is a register to register instruction set where you have operations which work on registers. And so the current architecture has 32 general purpose registers that it can hold a double word or a word. And some of these you should really be familiar with, right? So the main things to be familiar with is the special ones, the zero register, the link register for holding the return address of the function, the stack pointer for holding local variables. Also, if we spill over the number of procedure arguments, then we can use that in the stack. In between 8 and 27 are temporary saved registers. That's about all you really need to remember from that. And then X0 through X7 are our argument registers for our function calls. And so the ARM or RISC architecture has these memory operations to move things to and from registers, and then therefore the rest of the instructions work solely within the registers, or having information encoded in the instructions, such as an immediate instruction in there. For dealing with data, we've got mainly in chapter 2, we'll leave floating point at chapter 3. So in chapter 2, we have integers and character data. For integers, we have unsigned values, right? So all of the bits are the value of the integer. And then we have for signed numbers, we've got twos complement. There are some other ones. So if we look in the textbook, he didn't put them in the slides, but there's ones complement and signed magnitude. All of those are used for doing signed integers. It's just that in a modern computer, the ones complement and the signed magnitude don't have the performance of the twos complement and the ease of use. And so twos complement is predominant nowadays in what's used in modern computers. But all three of those formats held signed values. So the highest magnitude bit is the signed bit, 0 for non-negative, 1 for negative. So for our instructions, let's see. So signed, unsigned, instructions, decisions, function stuff. There's actually a whole bunch of things here for functions, and then we'll talk character data. So instructions in the computer and branching. So if I take a look. So the instructions in the ARM architecture are fixed in size, 32 bits. That's a word. Small number of formats. We've only got 6 formats. And so we've got our logic arithmetic operations, We've got our data transfer operations. We've got our logic, arithmetic operations with one less register with an immediate encoded in it. And there's also the immediate wide. I'll mention that and remind myself when I see the slide. But then if we move forward to branching, we have two types, unconditional and conditional branching. It goes to a label, L1, L2, maybe some better name than that. And the compiler, the assembler, will take care of translating that into a numeric value, which represents the actual distance in bytes from one location to another location. Testing a register if it's 0 or not 0, or unconditionally branching to a point. Lets us do if statements, loops. If we need more conditional operations, then we do have that supported, right? Equal, not equal, less than, greater than. So we have a branch operation to support those. So the two big register-based things to think about was actually no, three. For procedure calls is for the typical argument list, we've got X0 through X7. For local storage, and if our argument list exceeds those 8 registers, we've got the stack pointer. And for returning from our function call, what we want to do is go to the next line of code after the call that called the function. So we need to have a reference to that. We put that in the link register X30. All right. So BL puts that address in X30. We jump, do the call, and then we come back using the link register to get back to the program counter and get off and running again. So in the program space, and we'll talk more about virtual memory in chapter 5, but in the program space, typically the program code is at the bottom end, the low address, and the high address is then where the stack starts, and in between there's some space generally set aside for dynamic data. And so in any good assembler, you've got to push and pop to push things on the stack and pop them back off again. Yeah. For character data, we have ASCII, which is byte-sized, Unicode, which is a variable length encoding, which includes backwards compatible to ASCII and also does other alphabets and symbols with a nominally 32-bit character set. But you can also go down to 16 or 8. All right, and don't forget the PDF has the different formats on there too, but they're here in the slide. But it might be easier to simply use the reference if you need to remember something. I don't think I asked about synchronization. Nope. Right. And this is a reminder of what I was talking about, where the text or the code is down here at the low address. The program counter is typically at the starting point, the main entry, the main function, and then it goes through step by step. On a ARM architecture, then that program counter is updated 4 bytes at a time, or a word. And then the stack is at the top, working its way down. I don't think I asked anything about instructions, supporting procedures, the link register, the stack pointer. I didn't ask anything about the frame pointer, communicating with people. So I didn't really ask anything about any of this stuff, so we can skip all that. Yeah, so there's a lot of stuff in chapter 2, but I'm not going to ask anything about the x86 or the MIPS or anything but sort of, what the book's focused on for doing assembly. And the instruction set architecture and data such as integers and ASCII data. All right, and then the final chapter for the exam is chapter 3, Arithmetic for Computers. So we're interested in integer operations, addition, subtraction, multiplication, division, the floating point standard, and then floating point operations. And then the third broad category would be subword parallelism, or SIMD type instructions. All right, so definitely be aware of overflow, right? If the numbers differ in sign for addition, we're not going to have overflow. Otherwise, if the signs are the same, then there is a possibility of overflow if I pick a large enough value for both operands. Subtraction, the rules are slightly different because we'll change the sign of one of the operands. So SIMD instructions are subword parallelism, is where we use short sets of data and apply the same instruction to them. In this description, we've got a 64-bit adder, so 8, 4, or 2 different sizes of data, or a number of elements. The more modern architecture has either 128 bits or 256 bits, so it can hold even larger values. For example, is 256 bits, I could do 4 doubles, or 32 8-bit values. For multimedia operations, typically, we're not as concerned with overflow, so we'll clip the value by simply setting, if there's an overflow, the result to the largest representable value, because we're also typically using positive values rather than sign values, because there's just a positive value for red, green, blue, or for an audio range. I don't remember really asking anything deep about the multiplication hardware or optimization, so we don't need to worry about that, right? It is interesting to note that to do multiplication, your simple asterisks in your high-level language gets translated into, could be multiple instructions. If I have a 64-bit register and I'm multiplying two 64-bit numbers, then I will exceed the size of that register very easily. So we would have to split it into a low and high. And then depending on whether it's signed or unsigned integers, we would have to have a signed or unsigned version. For division, then we just simply have a signed or unsigned, right? When we're dividing two numbers, we're going to end up with a smaller number, and therefore we won't worry about needing more bits to put the final result in. So for floating point, there have been a number of representations, but the current standard focuses on giving two representations, single and double precision, and there's some auxiliary representations too, but the primary ones that we expect to see supported on all the hardware that implements IEEE standard is they must support the single and double precision. And so we will have a biased exponent so that the exponent is unsigned. And then we'll have a fractional bit. And of course, a positive exponent is a really large number. A negative exponent before the bias is a fractional number being represented on our computer. I don't really ask you about the range of precision. And I didn't ask anything about subnormals. There is support in the standard for the different other representations, like special things such as infinity, not a number, for illegal operations. And in fact, a few languages do support that, like Python. My old favorite C doesn't really support any of that, so it just simply crashes. Let's see, what else did I mention here? Addition, subtraction, a sort of high-level view of multiplication, division, the floating point standard, not a number, and then subword parallelism. So there's a few more slides talking about that. Let's see. So typically the floating point hardware is separate from the CPU, though it's in the CPU chip nowadays, but it's separate from the CPU core. And it does its own part because it takes several clock cycles, so you don't want it to impact regular operations. And nowadays, to further support this, in addition to our general purpose registers, we've got our floating point registers, and then in the modern Neon architecture, those are subsumed into the Neon's vector registers, where they can be used for floating point operations, integer operations, or the SIMD subword parallelism operations. don't think I asked anything about that, right? Other names for subword parallelism, vector parallelism, data level parallelism, SIMD instructions. And like I said, there's a set of registers for that, which does integer and floating point. And there are quite a few instructions to do SIMD type operations, 245, right? So a good quarter of the instructions that are there from the original 45 to 1,000 plus instructions are just devoted to the SIMD type operations. Right. The strided load is talking about being able to take rows or columns from matrices or arrays and slapping them into our vector registers and doing it in a very efficient manner. And so all of this is really, again, getting the best performance so that our benchmarks look good and that we do these type of typical operations as fast as possible. Even though these are sort of outside the purview of our original set of basic operations. We don't ask anything about the x86. Bits have no meaning, and our instruction set architecture supports arithmetic. Plus, operations can overflow and underflow. So that's just a very, very, very high level overview of things to focus on. Go back and reread, or if you've read it, skim back over it to refamiliarize yourself. And then also realize you have plenty of time on Wednesday to take the test. So get plenty of rest beforehand. That would be my recommendation. Get a good night's sleep, a good meal in before you sit down and take the test. It's open book, so you can reference the book material. Any of the other material on the Blackboard website, and knock the test out in your own time, but make sure to not let anything time out or anything like that. And then once you're done, you're all set and you can enjoy spring break. So unless you have any questions about anything we've covered, or any questions at all about the class or anything like that.
I was just wondering, are there multiple like problems, calculations that you need to do? So we have calculators.
No, I left all that for the homework, right?
Okay.
So that is a good point. So the homework is different from the test, right? So the homework, I asked things like the K-map, and I did ask a lot of questions where you did math and equations. Don't use really the homework as an example for studying for the test, right? The homework, I asked a certain set of types of questions. The test, I asked a different set of questions. Does that make sense?
So the test is going to be more about applying what you've learned from the basic concept?
Correct.
Okay.
So I am recording this, so it'll be up there, so you can always go back and review this again over the weekend, or I guess, no, we only have a couple of days. And of course, also, this review sheet is under here, under exam reviews. So use that as a guide to, I would, print it out or have an open piece of like a Word document, either way, whatever works best for you, and just make a few notes in the Word document or make a few notes on a printed out copy of the exam review and use that as a way to work yourself through the various chapter and section headings. And then once you complete it, you go, okay, I'm done with studying and I can move on to other things. Does that make sense? Because you don't want to get too obsessed about it. Take it from me. I think of all of us, I have probably taken more tests than anybody else since I have completed a bachelor's and a master's and a PhD. So believe me, I had to take a lot of tests over the years. I think the hardest test I ever had was the professor gave us the test and said, come back in 2 weeks. Was the test complete? This was in grad school. I had 2 weeks to work on the test and I made a C. So tests can be arbitrarily hard or easy depending on how things are. I think this one should be straightforward. It's also not long form. It's simply multiple choice, an open book. So if you don't have any other questions, then I'll be around for chat on Wednesday. Otherwise, knock the test out and then have a good spring break.
Hey everybody, it's Lon Seidman. We are back with the Mac Mini, the new M4 one, because a lot of folks in my original review were curious about how the Mac Mini might stack up as a Plex server. After all, there is a native version of the Plex server for Apple Silicon-based devices, which this one, of course, is powered by, and a lot of you are wondering how well it might perform. So we're going to find out today, running a couple of different video scenarios, and what we'll do is compare in real time how those videos transcode on the Mac versus a super cheap GM-K-Tech N100-based mini PC. We last featured this in my Linux server on the cheap video, where you can see just how effective this really low-cost computer can be at hardware transcoding. In fact, it was even doing HDR to SDR tone mapping off of a 4K video in real time with plenty of room to spare insofar as what its processor was handling. So I was very impressed with this, and we'll see how the Mac holds up here doing the same tasks on both. And to do this, we're going to play back a couple of different videos. One is a regular Blu-ray rip, a 1080p Blu-ray. We're also going to look at a 4K Blu-ray and doing hardware tone mapping again, along with transcoding. And we'll also look at an AV1 file because a few people were interested in that as well. And in all of these instances, we're going to have the two computers playing back the video, transcoding it down to 720p. So we'll put both of these things here through a bit of a workout. So I'm eager to see how they stack up against each other. And before we jump into this, I do want to let you know, in the interest of full disclosure, that this is not a paid sponsorship by Plex, although they do occasionally sponsor videos here on the channel. I will, they'll leave an affiliate link in the video description for a Plex Pass, which is what you need to do hardware transcoding on these devices. I also want to add that the GM-K-Tech PC here was sent to the channel free of charge by GM-K-Tech. However, they are not sponsoring this video either, and I bought the Mac here with my own funds. No one has reviewed or approved what you're about to see before it was uploaded, and all the opinions you're about to hear are my own. So let's get into it now and see how these two devices stack up when it comes to Plex hardware transcoding. All right, so we're going to start off here with a Blu-ray MKV file. Both of these machines are playing the same exact Blu-ray rip, and as you can see, both are currently hardware transcoding down to 720p at 4 megabits per second. And if we stack up the two charts here, you can see that both are very efficient in that activity. What I'm going to do here is actually just jump both of these machines that's playing back to the midpoint here and see what that does to our server usage.
Came back because
Anybody looking for me?
Barbara Brown.
Crime. It's usually quite busy there.
She's like, don't just stand there and look, help me, nigga.
Hello there, and welcome to the 204th edition of DF Direct Weekly. It's our show where we discuss the latest gaming and technology news. And man, sometimes a week seems to pass with nothing happening, and then everything happens just before we record. So it is this week. Joining me on the panel, first of all, Oliver Mackenzie. Hello.
Yes, hi Rich. I'm reporting in from a new location, but it's always excited to chat the topics of the week. And like you said, there are some big ones this week, so it should be fun.
Yes, some meaty discussion points for sure. And Alex Battaglia. Hello.
Yeah, I'm recording from the same old location. Nothing new.
Yep.
But big AMD week. AMD strikes
Absolutely.
back. It's great.
On multiple fronts. And it's all good stuff. So with that, I guess we should just crack on. Okay, so our key news story of the week, and this one is quite fascinating. Obviously, RDNA 4 GPUs released this week. We also had the official unveiling of FSR4 upscaling, which Alex did a video on, and even from preliminary testing, this is looking really, really impressive. Now, interesting thing happened the day before we filmed this, which is to say that AMD strongly hinted that Sony was involved in the creation of FSR4. And we've actually had the chance to get some comments from Mark Cerny on this. He's answered some questions that we put forward there. And the results are highly enlightening. And I guess the key point is that the headline statement, so to speak, is that Sony is looking to integrate some kind of iteration of FSR4 into 2026 PlayStation 5 Pro titles. But there's a lot more to it than that. Oliver, we want to take up the story?
Yes, this is really encouraging, I think. Basically, in our comments and Q&A with Mark Cerny here, he's suggesting that indeed for 2026 titles, they're going to implement basically the neural network from FSR4 into a version of PSSR for the PS5 Pro here for 2026 titles. And I think this is really encouraging, ultimately, beyond any like technical aspect of it, because like we've seen from the first few months of PS5 Pro titles, PSSR is a very imperfect solution for AI upscaling relative to solutions from competitors. It is competitive in some respect with FSR2 in a lot of titles, and it can be a fair deal better in some scenarios, but it's not doing a good job of delivering a consistently clear, smooth, stable image in motion and in stills. We've seen some improvements from launch with new versions of PSSR, but they haven't really improved on, I would say, like the fundamental areas of weakness of PSSR. They've more improved on like SSR resolve, or like the foliage is touched up a bit, like some of the more egregious areas of the technique, but they haven't really brought it up to parity with those other techniques or anywhere close to that level, really. But FSR4 on the other hand was super impressive. I mean, I saw this in person with Alex at CES. We spent about 20 minutes poking around Ratchet and Clank. Alex is obviously an expert at finding the various issues in that title, and obviously Alex's coverage since then has shown that the technique is super impressive. And I was kind of worried here that the PS5 Pro might not have the performance to pull off FSR4 because the machine learning performance of RDNA 4 seems greater than the PS5 Pro here. But it sounds like a version should be achievable in the hardware. At least that's what they're aiming for. Their language is a little bit tentative here, I would say, but that's certainly their aim here. So I think ultimately, you know, with PS5 Pro here, a lot of our concerns, I feel like, were localized that initial batch of PS5 Pro titles, and I think we made a point of saying this, which is that the hardware is quite compelling, but the technique they were using for machine learning upscaling that hardware was not quite up to snuff compared to competitor solutions. And what we've seen from that hardware in terms of the ray tracing acceleration, which we know is quite similar to the ray tracing acceleration that's present in RDNA 4, was actually pretty decent. Like we are seeing ray tracing, enhanced ray tracing in a number of titles, including the recent Monster Hunter Wilds and Assassin's Creed Shadows. Both those titles have RT reflections on PS5 Pro, whereas the base consoles don't have RT reflections. So yeah, I'm really encouraged to see that. I think it sets Sony up really well for PS6 potentially, getting these technologies in place for their next generation console early, effectively. And yeah, I'm really, really encouraged to see this. I'm really, really glad to see this. I was wondering if maybe FSR4 in some capacity would be able to run PS5 Pro here. It seems like that is indeed the case, and it should mean really good things, hopefully, for image quality in PS5 Pro software.
Mm-hmm. Yeah, I mean, essentially, Alex, there are differences in terms of the machine learning implementation, which is custom on Sony and obviously AMD specific on AMD. Do you have any sort of comments on that? On you know this concept of moving the model across from FSR4 to PlayStation there?
Yeah, there's we have some great confirmation of some things that I speculated on, and I'm willing to say, yeah, I was wrong about that. Mark Cerny makes mention that the PlayStation 5 Pro's 300 tops figure for its integer 8 kind of theoretical top speed there is actually in reference to it without sparsity. It doesn't make mention of it actually supporting sparsity on the PlayStation 5 Pro. And sparsity basically was a way, at least NVIDIA, back in the day when, I think it was when Ampere came out, that they revised the DLSS 2 model at the time, and they improved the speed specifically on Ampere and above. And that's kind of what got into like the sub 1 millisecond range, at least for that DLSS CNN model. So we have confirmation there that PS5 Pro does have 300 tops of int 8, which would put it behind, without sparsity, which would put it a little bit behind RDNA 4 for those calculations. Based on some AMD patents that are circulating, it appears that we may be seeing some sort of like hybridized model here, targeting RDNA 4 for FSR4, that may be somewhere in between and utilizing features of both the CNN and a transformer model, but it specifically may be accelerated by FP8 instructions, which is something that wasn't commented at all on in any of the PS5 Pro disclosures, but it is something that is new, for example, to RDNA 4. So the whole tentative wording here that Oliver talked about, and the fact that it's like 2026 tells me, like, or at least my conjecture would be that the timelines once again are not like completely lined up. You know, Sony had to shoot first, and they had to target different hardware at first. Like the size of the CU would be a lot bigger if it was more like the CUs we'd see in an RDNA 4 GPU that supported maybe more instructions. So maybe, as conjecture here, Sony doesn't support the specific acceleration which currently FSR4 is using on RDNA 4 on PC. So there's going to be maybe an elongated porting process to get it up to snuff in terms of quality and performance, because that's another thing that Cerny mentions in this interview, is that they want to have it being used in titles that are targeting 60 FPS. If it exceeds a certain millisecond threshold, 60 FPS becomes a lot less viable, right? So I'm very curious to see what the end product looks like, if it does look like FSR4 in all of its aspects. To say the least, FSR4 for me was amazing looking in person, seeing it running. I only was able to try it in the Nixies games, essentially, because that's where FSR 3.1 support was just perfect. I had trouble with other titles, actually. But there it worked really, really well, and the quality was incredible, really stable, more stable than DLSS 4 in some areas that I pointed out in the video. And with less artifacting too. I also showed off DLSS 4 transformer model can show striations in images that I kind of also pointed out in the ray reconstruction video I did. So it's like very stable and really good at anti-aliasing, which I really like to see, because I actually prefer images that are even a bit softer with better anti-aliasing than those that are like a lot sharper but have trouble with anti-aliasing. So I actually really like FSR 4's resolve quite a bit. And I would like to see if PSSR could get to that kind of level of stability and quality that I saw there. But I guess we're gonna have to wait like a year or so to see what that might look like.
Yeah, indeed. I mean, Oliver, you were asking Mark what the short and long term goals are with Amethyst, and we got some quite interesting information there.
Yeah, I mean, it sounds like in the short term, their goal is basically to develop mostly neural network architectures here for game graphics. And that certainly was an area of some conversation when I spoke to Mark back in October of last year. And then in the long term, their goal is basically to work on hardware designs, which makes sense given that Amethyst, I believe, started about a year ago, that collaboration, they said. And looking forward, that would certainly presumably be involved to some degree in the creation of, let's say, a next generation PlayStation console, and presumably would not factor as much into the hardware design, if at all, I would assume, of the PS5 Pro. That was probably locked down before most of this Amethyst collaboration started. So I would hope that in the short term, we're going to see something like Alex said, some kind of variation on FSR 4 for the PlayStation 5 Pro console, and then presumably for the PlayStation 6 as well down the line, and then some additional level of hardware collaboration to hopefully improve the state of future Sony hardware here. And I think certainly at least this, as a first output potentially from this Amethyst collaboration between Sony and AMD here, seeing FSR 4 on PC certainly indicates that perhaps this will be a fruitful partnership, hopefully.
Yeah, absolutely. Interesting disclosure there that they're looking for a more ideal hardware architecture for machine learning. So, obviously a collaboration with the intent of producing something that applies to all markets there. Something which also caught my eye was a hint, I guess. I mean, we were basically asking if the denoising demo that you guys saw, and I guess it was is it the Toy Shop demo?
Yeah.
Was that a part of Amethyst? Mark Cerny says, all I can say is stay tuned. There's a lot of opportunity with our Amethyst collaboration. We know that ray tracing is a huge part of the graphics future. So from my perspective, it's quite interesting that, let's be clear here. NVIDIA has laid down basically almost like the roadmap for ray tracing and AI features. And they've kind of paid off. I mean, ray reconstruction is pretty excellent. The whole ray tracing suite they've come up with, the integration with ML, it's all sort of paying off. And then we've got Amethyst, which is essentially producing very similar technologies. Is there any sort of final words on this, Alex? Because it's quite intriguing to see this come out.
Yeah, I mean, just in general, we know the cost of running all these ML things on the GPU is still expensive, even with proper acceleration. We saw, RDNA 4 RX 9070 XT had I would say, measurable performance cost of running it. Then you go over on the NVIDIA side, and in a game that has kind of like lackluster, I would describe it, quality of denoising, if you turn on ray reconstruction there, you'll often find that ray reconstruction, and definitely the transformer model, is a lot more expensive than normal denoising. So you're getting much higher quality, but it's also more expensive. And that's one thing that I'm very curious to see, based upon this set of questions and answers from Mark Cerny here, how much of that is like realistically portable to games on the console, because there's just many more constraints there for performance that where on a PC you can say like, I'll be with VRR, G-Sync, MFG, whatever, you just throw all these other things on top to try and make it worthwhile, right? Whereas on console, it's like, no, we got to hit like a 60 V-Sync, right? So it's a different environment. So I'm very curious to see what that means to that. But for the more long-term future, I'm extremely happy now that FSR 4 in some form is going to be coming to PSSR, even if it ends up like not being all the way there for the first implementation. We at least know that PS6 will definitely have the hardware based on what we see in RDNA 4 to run it in full, big form, whatever. So good times ahead.
Well, you would assume that PS6 would be using some custom variant of UDNA, which is the next generation architecture. So, exciting times ahead. We know almost nothing about it, really. But I'm sure it's going to be really interesting to see how it all plays out. But with that, let's move on. Staying with AMD, this week, of course, we saw the release of RDNA 4, the 9070 XT and the 9070. My review's out. I was actually really heartened to see that we got our FSR and FSR 4 video out actually before my review, which was I think everybody really wanted to know what Alex thought of it. Because we had that tease at CES where it was like, hey, this is looking really, really impressive, but would it stand up to the direct feed capture scrutiny? And the answer is yes, it does. Actually, Alex, that's an interesting point, because obviously a lot of the time when you do your
dominant nowadays, and
deep dives into image reconstruction techniques. People are kind of criticizing you for this